Hello, ladies and gentlemen. We're going to pick up in section 1-2 talking about domains of a function. So we've done this visually, and I'm going to try and bring the graphs in there so you can see them, but you need to understand what's happening algebraically. So let me first talk to you and say that the main things that we are looking for when we're talking about the domain of a function are sort of ways that you could break the function. What are x values you could not plug in? So the two biggest things that we see are the radicand, that's the part underneath the square root, must be non-negative. You cannot take the square root of a negative number. That's the big thing. The other thing is the denominator can't be 0. And we've talked about types of discontinuities, and those things are going to show up here. But we're going to combine them into this idea of describing the domain using interval notation. So as a reminder, if we're including the endpoints, we use brackets or think like closed circle. And if we're not, we're going to use parentheses. And infinity is always going to be parentheses. You're never counting to infinity. So let's do a couple problems together and see if this makes sense. So the first one, it says find the domain of the function. Now I am going to draw these on a number line, and I'm going to draw them, look at the picture as well so you can kind of see. The main things I'm looking for are, is there a denominator, because the denominator can't be 0, and is there a square root? And the answer to both of these questions is no. So if you just give me a line and I say, well, how far left and right does this thing go? It goes left forever, and it goes right forever, and there's no holes in the middle, so the domain of this would be from negative infinity to positive infinity. There's nothing wrong with the domain. You could say all real numbers. If you've ever seen that symbol, that means all real numbers. But in interval notation, we'll say negative infinity to positive infinity. I can plug whatever I want in there, and I will just get x. On a number line, the way I would draw that, and this is kind of silly, but on a number line, you're like, well, it goes forever to the left and the right. Oh, that's not a line. Let's try this again. So we'll just draw it, and we'll say, here's my domain. It goes forever left. It goes forever right. So the domain is all real numbers. Cool. The square root of x. All right, so now we got to think. You cannot take the square root of a negative number. So this radicand, that's the part underneath the square root, it can't be negative. It can be 0 because you can take the square root of 0, but it can't be negative. So what I'm going to do is take the radicand, whatever it is, and in this problem it's just x, but I'm just going to say it has to be greater than or equal to 0. Whatever's under the square root has to be greater than or equal to 0. It can't be negative. It can be 0, it has to be positive, or 0. So whatever's under the square root, well, in this problem it's just x. So the domain for my inequality is x is greater than or equal to 0. And if you look at the picture, if I said, where are the x values? Oh, sorry for the bell. Why are there bells today? There's nobody here. Okay, so all of the x's that are greater than or equal to 0, you look at the graph, it doesn't start until right there at 0, 0. That's the first x value that you can plug in. And if you think about y, if I try and plug in -1, then I have the square root of -1, and that's imaginary. So we're talking about real numbers here. That's not going to work. You can't plug any number that is smaller than 0 in, so you have to say, well, then x has to be greater than or equal to 0. In interval notation, the way we say that is from 0 to infinity, and 0 is going to be a bracket because it's like a closed circle, so from 0 to infinity. On a number line, the way I would draw that is I would put 0 on my number line, and then I would put a closed circle at 0, and I would draw all the numbers that are bigger than or equal to 0, so I'll draw to the right, and then describe that in interval notation again from 0 to infinity. All right, this one has a denominator. So we've talked about discontinuities before. You want to figure out where the denominator is 0 because x minus 4 can't be 0. If it is, then you're dividing by 0, which means x can't be 4. Now you should remember that since this factor did not cancel out, this is called an infinite discontinuity. We see infinite discontinuities in the graph as vertical asymptotes. So you can see there's a vertical asymptote at 4, but now we're going to describe the domain. And what I'm going to kind of do is just draw a number line to help me. I have the picture as well, but 0, or I'm sorry, not 0, I'm going to put 4 on my number line and say, anything I want left of 4 works. Like all these numbers, it goes forever to the left. And it goes forever to the right. The only time I have to pick up my pencil is at 0. So if I were to sketch this on a number line, I'd say, well, it goes forever to the left, it goes forever to the right. The only thing that doesn't work is 4, so I'm going to put an open circle at 4. Now to describe that in interval notation, we'll just do this piece. We'd say from negative infinity to 4, and those are both parentheses because they're open circles and they're infinity. Union, then you put your pencil back down at 4, and then you shade forever to the right. So from negative infinity, forever left, to 4, pick up your pencil. Back at 4, you can put your pencil back down, and then forever to the right. So it's from negative infinity to 4 and 4 to positive infinity. That's the domain. You can plug any number in here except for 4. This one's going to combine some ideas, so now we're starting to kick it up a little bit. Let's first talk about the radical. We know that whatever is underneath the radical has to be greater than or equal to 0. In this problem, that's x plus 1. So that means x has to be greater than or equal to negative 1. Now if you look at the graph, you can see that it just stops at negative 1, because if you try and plug in, for example, negative 2, then you end up taking the square root of negative 1, and then you're like, well, that's not real, so I can stop. So you can see in the graph that the first x value we have is at negative 1. And we're going to say, well, it has to go to the right of that. You can't pick anything smaller than negative 1, or then you take the square root of a negative. But this one also has a denominator. And the denominator, x squared plus, or minus 5x plus 6, cannot be 0. Now I'm going to factor this. That's x minus 3, x minus 2. That means that x cannot be 3 and x cannot be 2. Not for anything to do with the radical, but because you can't divide by 0. So it has nothing to do with the fact that there's a square root in the top. It just matters that there's a denominator that can't be 0. But they're both in this problem. So what we're trying to say is you have to pick all the numbers that are greater than or equal to negative 1, but you can't pick 3 or 2. And you can see in our graph, 3 and 2 have vertical asymptotes. Those are infinite discontinuities. So the way I'm going to say this, I'm going to draw it on the number line again and say, all right, I want to put the 3 things I care about are negative 1, positive 2, and positive 3. And I know that these are open circles because it can't be 2 or 3. Then you're dividing by 0. But it can be equal to negative 1, because if you plug in negative 1, you'll get 0, and the square root of 0 is 0, so it'll be 0 divided by whatever, which is 0. So negative 1 does work. I can see it right there. I want all the numbers that are greater than or equal to negative 1, so that's these guys. But again, you got to pick up your pencil at 2 and 3 for those vertical asymptotes. So this is my domain, which is a little more complicated to describe because you can tell there's 1, 2, 3 intervals I have to write. So the first part of the domain will be right here, from negative 1 to 2. 2 has parentheses, negative 1 has a bracket. Union. This middle one is between 2 and 3, and those are both open circles. Union. Then this guy, from 3 to infinity. You can see it in the graph. This is from negative 1 to positive 2, right there. You pick up your pencil at 2 because it's a vertical asymptote. From 2 to 3, these are the x values from 2 to 3, but again, you have vertical asymptotes, so you have to pick up your pencil. And then from 3 to forever to the right, positive infinity. So you combine both ideas here. It has to be bigger than negative 1 because you can't square root a negative, but it can't be 2 or 3 because you can't divide by 0. So that's about as hard as I get. Let's try a couple practice problems. This one says, write the domain using interval notation. They give me a little spot for the number line, a little spot for the domain. Now, I can look at this one and tell you it's all real numbers, which I'm going to write as negative infinity to positive infinity. Because this is a parabola. There's no denominator, and there's no square root, so there's nothing I can do to plug this, to break this function, essentially. You look at the graph, and you can see it goes forever to the left and forever to the right. There's no discontinuities. On a number line, I would just draw it like this. Say, this is kind of lame, but there you go. There's your number line. I guess I could put 0 in the middle. Just say no. Okay. All real numbers. Anything works. It's a parabola. You can square anything and then add 3 times or whatever. It's fine. So, fine. This has got a square root, though. So, jeez. The radicand, the part underneath the square root, x minus 7, has to be non-negative. The way we say non-negative in algebra is greater than or equal to 0. Which means x has to be greater than or equal to 7. On a number line, I would say you can start graphing at 7, and then you want all the numbers that are bigger than 7, so we would go to the right. You can see in the picture here that the first time that there's an x value is at 7, so it seems to be matching up with my algebra, and I'm going to say the domain is then from 7 to infinity, and 7 has a bracket because you can plug in 7. A reminder why. 7 minus 7 is 0. The square root of 0 is 0. That's fine. It's not imaginary. We're cool. So from 7 to infinity is the domain. This one looks like I'm going to have both ideas. I know I have a radicand, so I have to set that greater than or equal to 0, which means you have to pick positive numbers or 0. And you know that x minus 5 can't be 0, which means x can't be 5. That is an infinite discontinuity. I can see it in my picture at 5. I have a vertical asymptote. And I can also see that the first x value that actually shows up is at 0, because if you try and plug in, for example, -1, you break it in the top. So you got both ideas again. You got to start at 0, and we're going to describe this interval, let's say from 0 to 5. I'm going to draw it on here. 0 to 5. 0 works. I can plug in 0. It's fine, because you'll just get 0. But I can't plug in 5 because I divide by 0. And I want all the numbers that are greater than 0, so that's to the right. And it's like saying, well, all the ones that are greater than 0 except for 5. So then these are my two intervals. You can see it right here from 0 to 5 and from 5 to infinity. And you can see it on your number line. So let's write it in interval notation. That would be from 0 to 5, bracket for 0, parentheses for 5, union, 5 to infinity. Both of those are parentheses. Couple more. I'm going to factor the denominator to figure out when it is 0, x plus 2, x plus 1. So that means that x can't be -2 and x can't be -1 because those are infinite discontinuities. You can see it in the graph. -2 and -1, we have vertical asymptotes. Cool. We're just going to put these two on our number line and say everything else is fine. You just can't plug in -2 or -1s. These are open circles. And what I'm going to do now is just say, well, look, to the left of that, sure, you can plug in negatives. That's cool. You can plug in between them. That's fine. You can see it's right there. Or you can plug in to the right. Also good. The only thing you cannot plug in are -2 and -1 because that causes you to divide by 0. So in interval notation, my domain is from -infinity to -2. That's this interval. From -2 to -1. That's this interval. And then from -1 to positive infinity. So you can see it in the graph, 1, 2, 3. This one's kind of down here, you can tell. You can see it in the number line I drew, -infinity to -2, -2 to 1, -1 to infinity. Or you can see in the algebra, everything but those two. Basically the way you say everything but those two is pick up your pencil at -2, and then pick up your pencil again at -1, and you just got to write that a couple times. Okay? One more. The cube root of x. Now, we talked about you can't take the square root of a negative. You also can't take the fourth root of a negative for the same reason. But cube roots are okay. You can take the cube root of a negative. For example, the cube root of -8 is -2. Since a negative times a negative times a negative is still a negative, even though these two cancel out, there's going to be one that sticks around. So with odd degree roots, you're not going to have any issue with the domain. Odd degree roots are fine. This is going to be all real numbers, which is -infinity to positive infinity. You can take the cube root of any number because there will be an odd amount of negatives. If you think about it, the two evens, the even amount of negatives will pair up, and so they'll cancel out and always be positive. But if you have that third or fifth or seventh or ninth or any amount of odd negatives, that one will always stick around and it'll make the answer negative. So if it's a cube root or a fifth root or seventh root, those odd roots, it's fine. You can take the cube root of anything. So there are no domain restrictions. You can see in the graph, yeah, we took the cube root of -4. We took the cube root of -2. We took the cube root of 0. They're all fine. There are no holes in the graph, which means the domain is all real numbers, and the way we say that in interval notation is from -infinity to infinity. I'll draw the number line just for posterity. There you go. And that is at 0. Okay? So, again, you're looking for where the radical is negative, and you're looking for where the denominator is 0, and you're going to say that these are going to be issues that I have to address in my graph, and if you can write them in interval notation, you got the domain. So, good luck.